Last topic, independent events, so probability. This also involves the word and.
Okay, everybody had a chance to sign up? Did it make its way around? No? Okay. So pick a day and we'll worry about times later. So events are independent if the outcome of event A has no effect on the outcome of event B. Events are independent. If the outcome of event A, or any event, right, some event, outcome event A has no effect on the outcome of event B. So if you think about dependent events, draw a card, don't replace it, right, and then draw another card. So that when we go to draw the second card, we're starting with a deck that's short one card, and it could be missing a king or something. That's a dependent event. In an independent event, there's two things that we need to look at. So either A and B are two totally different things, right? So if we're talking about event A and event B, then either A and B are two totally different things. So this is one of the questions you're going to have to ask yourself when you're doing a problem is this a dependent event or an independent event? Right? Dependent events you'll see without replacement usually, right? Just think about it. I'm starting with, when I go to do the second thing, something has changed. If I have either A and B are two totally different events, so for example, could be rolling a die and tossing a coin. So if you roll a die and toss a coin, then it doesn't matter how the die comes up. That has no effect on the coin, because the coin is something totally different, right? It's independent. Or drawing a card and tossing a coin. You could draw a card and toss a coin. Again, two totally different things. So if you're reading the scenario and you say, those are two totally different things, then you know you're dealing with an independent event, right? Independent events. Or, so what if the same thing is happening? So if A and B involve the same thing, like drawing cards or whatever, if A and B involve the same thing, then you're going to see the words with replacement. Okay, you will see you will see the words with replacement, or something that implies this. You draw a card, you put it back, and then you draw another card, right? Putting it back is replacing it. Okay, which means that when you do the second event, you're starting with a full deck of cards. So if you're doing the same thing, right? So it's like draw a card, put it back, draw another card. So draw a card, put it back. So some synonym for replacement, something that implies you're replacing it, put it back, draw a card. Draw a marble out of a bag of marbles. Put it back. Let's just say replace it. And then draw a marble. So remember, back to dependent, we were drawing a marble from the bag, and there were like 3 reds and 2 blues. We drew a marble. Well, there were 5 to begin with. Now there are only 4. Okay, now there are only 2 reds instead of 3 reds, right? So that's a dependent event. That's the one that goes probability of A times the probability of B given A. So that's one of the formulas that you see. Or if you're looking at a Math 20-1 formula sheet. anyways, on the formula sheet, on the formula sheet, you'll see the probability that we gave the other day, and you're also going to see these probabilities I'm going to show you in a second. And then what goes on with this involves the same things. It's back to the initial starting conditions. So they are independent if you are back to the initial starting conditions. So if it's draw a card, put it back, that means you're starting with a full deck, right? So independent events, you'd always be playing with a full deck. Draw a card, take a look, put it back, you're starting with a full deck. Draw a marble, take a look at it, put it back, you're starting with a bag full of marbles, right? Whatever was there initially is there now. All right, that's what makes independent events. You get a formula which looks like this. A intersect B is equal to P of A times P of B. Okay, so you just multiply the two probabilities together. In words, so one of the things you might want to do when you sit down and get the exam, and they're going to tell you to fill in this, that, and the other, rip out the formula sheet that's in the back, so you can fold the page out, tear out the formula sheet. You see that symbol, the intersection symbol, you might just want to write the word and next to it, and you see the union symbol, you might want to write the word or next to it. Just to remind you, okay, you've got two formulas for P, A, and B. The other one is for dependent events, which goes P of A times P of B given A, right? Looks like this, P of A times P of B given A. Okay, that's for dependent. This is for independent. What makes it dependent? You're starting with a different set of conditions. You're always doing the same thing, right? Dependent events can't be toss a coin, roll a die. Right? So wait, why does one depend on the other? It doesn't. Okay, examples. A coin is tossed and a single six-sided die is rolled. Find the probability of getting heads and rolling a 3. So a coin is tossed. And a single six-sided die is rolled. Now, sometimes they like to bring spinners in, so you've all seen spinners, right? The thing you flick the arrow and it spins, and you've got different colors or different numbers on the spinner. Okay, and be aware, sometimes if they do show a spinner, maybe the probability of a 1, like it's got a larger sector, maybe it's split into 5, but 2 of those are a 1. So the probability of getting 1 becomes 2 out of 5 instead of like 1 out of 5. Okay. So a coin is tossed and a single six-sided dice is rolled. Determine the probability of getting ahead and rolling a. Let's change the thing. Rolling a. That's rolling a 3. Okay. All right, so the first thing you're going to ask yourself, are these dependent or independent? And you say it's two totally different things. These are independent. So the probability of getting ahead by tossing the coin and rolling a 3. This is independent, so it's probability of getting ahead times the probability of rolling a 3. What's the probability of getting ahead? Depends on how hard you work. If you want to get ahead, you got to study. Exam coming up. 1/2. Probability of rolling a 3. How many 3s are there on a six-sided die? 1 out of 6. Half times a 6th. 1/12. Okay. So a lot of times they're going to give you probabilities as reduced fractions, just easier to work with. 1/12 is a decimal, it's just kind of ugly. And right? But 1/12 as a fraction is kind of nice, just 1/12. Remember, they can ask you probability using combinatorics notation. Okay, so everything we've done over the last 3 units can be combined, right? Set theory with counting, with probability. All of this comes together now, right? That's why you're going to look at that exam. Half that exam was like probability. Now, it was like set theory and counting and probability, right? But they go together. A card is chosen at random, replaced, and then a second card is chosen. So a card is chosen at random. Replaced. And then a second card is chosen. And then a second card is chosen. What is the probability of choosing a jack and then an 8? Okay, are these independent events? Yeah, because that's all we're doing today. But okay, remember, when you're reading through the events on the test, or on the exam, because on the test, the independent are all going to be together. But on the exam, you have to, is this dependent or is this independent, right? Is this mutually exclusive or not mutually exclusive? What word goes with mutually exclusive? Or, right? So you've got or probabilities, and you've got and probabilities. And probabilities go with dependent and independent. Or probabilities go with mutually exclusive, not mutually exclusive. Mutually exclusive goes with a Venn diagram where there's nothing in the intersection, or you have two circles that don't interlock, right? It's mutually exclusive. It can't be both. Non-mutually exclusive, there is an overlap, and there's something in there. Those are your OR formulas, right? P of A or B. A union B is equal to P of A plus P of B. Or P of A union B is P of A plus P of B minus P of A intersect B. Okay. Anyway, a jack and then an 8. Now, watch the wording, because it matters if I say a jack and then an 8, or if I say what's the probability one of the cards was a jack and one of the cards was an 8. Okay. If I say jack then 8, you have to get a jack on the first draw, and then you have to get an 8. Okay, so it's just this, right? So it's the probability of getting a jack times the probability of getting an 8. What's the probability of getting a jack? 4 out of 52. What's the probability of getting an 8? Okay, remember, we put the card back, right? So there are still 4 jacks in the deck. Not that it matters, but there are 4 jacks in the deck. But there are 52 cards in the deck when you go to draw the second card. So 4 out of 52 times 4 out of 52 is 1 out of 169. So what's the probability of getting an 8 and then a jack? What if we reverse the order? We'd say, well, what if you get an 8 first and then a jack second? It's going to be the same, right? So what if we change the question? And instead of saying, what's the probability of getting a jack then an 8, we say, what's the probability in the 2 draws that one of the cards was a jack and one of the cards was an 8? What must you now do? So think about it. If all I want is, if I want a specific order, jack then 8, or 8 then jack, this is how I do it. What if I don't care about the order? I just want to know that one of them was a jack and one of them was an ace. So you could say, well, then here's what happened. I either got this or I got this. So I got a jack and then an 8, or I got an 8 and then a jack. What do we do with an OR probability? We add them together, right? So usually it's just kind of like double this probability, right? Because it's independent events, right? So then jack then 8 just means one of these 4 out of 52 cards and one of these 4 out of 52 cards, right? It could be queen and then king. So watch, the wording to watch for is the and then, right? Is there something that implies that it must happen in that order, right? If not, then you've got to go to this bottom part and say, well, either you got this, then this, or you got this, then this, right? We'll do a couple more along those lines. A jar of marbles contains 3 red, 5 green, 2 blue, and 6 yellow. So a jar of marbles contains 3 red, 5 green, 2 blue, and 6 yellow marbles. Sometimes money is no object and they print the exam in color. But I think money is more of an object now, so who knows if there'll be some color on there. Well, if they go to full online, then they'll probably use a lot of color, right? Because that's cheap. A marble is chosen at random from the jar. So here's what's happening, right? This lays out the scenario. This is what we're dealing with. We've got this jar of marbles. This is what's in it. Here's what's happening. A marble is chosen at random from the jar. After replacing it, let's just say after putting it back, a second marble is chosen. Okay, so that'll be in the box. You see this box says use following information to answer the next 3 questions. Right, and then so it's like, okay, I've got this jar full of marbles, and I draw a marble, I put it back, and I draw a marble. And then we've got 3 questions coming. First question. Determine the probability of choosing green, then yellow. Okay, so they're independent events, right? Because we, after putting it back, so replacing it, we drew another one. Green, then yellow, it says it's got to be in that order. Your first marble is green, and then your second marble is yellow. So we can start off with the formula. Probability of getting a green and then a yellow is simply the probability of a green times the probability of yellow. What's the probability of getting a green? 5 out of 16, right? So we do 3, 8, 10, there's 16 marbles, 5 of which are green. And then probability of getting yellow. Sorry? If it were dependent, if we didn't put it back, it would be 6 out of 15. After putting it back. Putting it back means how many marbles are in the bag when I go to do the second draw. All of them, right? So 16. Okay, and then we just work this out and reduce the probability. Works out to 15 out of 128. Okay, so on your calculator, you just go bracket 5 divided by 16, bracket 6 divided by 16, bracket, math, enter, and you'll get 15 out of 128, right? We'll just go right to the reduced fraction. What's the probability of choosing yellow than green? Yeah, it's exactly the same. Okay, so it's the same, but if we write it out, we're going to go probability of yellow and green is equal to the probability of yellow times the probability of green, which is 6 out of 16, times 5 out of 16, which is 15 out of 128. And the last question, which likely on an exam would be the only question, right? So instead of asking these first two, here's a way to ask just one question, right? After choosing the marbles, what is the probability that one was yellow and one was green? So what's the probability that you got one yellow one and one green one? Now what if this were the only question? Why are you adding things? Okay, what is it? So it's just 15 out of 64, right? You're just going to add these two together. Gives you 30 out of 128, reduces to 15 out of 64. Same page. So you say, well, either, if I got a green and yellow, then either I got a yellow followed by a green, right, which is this guy, or I got a green followed by a yellow, which is this guy, right? The way you're going to work it out is just work out one of those and then multiply it by 2. Just say, well, I just need to work out one of these. I know that it going the other way around is going to be the exact same probability. And that works out to 30 out of 128, or 15 out of 64. Okay. Now, if we want to amp it up a bit, it could say, what's the probability of getting a yellow then a green, or a green then a blue? Right. Then you've got to work out yellow then green, or, which means you're adding green then blue. Okay, so if events A and B, gentlemen, take it in the hall, go to the cafeteria, you have my blessing, I will not mark you absent. Shut up or leave. Okay, so if events A and B are independent events, so given that A and B, so there are questions like this that you may see, and they're not easy ones. So given that A and B are independent events Okay, now another variation of this question is they give you some probabilities and say, are these independent events, right? And then you have to say, well, if they're independent, then the probability of A and B is P of A times P of B. Given the numbers they gave me, is this a true statement, right? If it's true, you could say, yeah, these are independent events. But I'm saying, given that events are independent, given the probability of A and B, right, A intersect B, of A and B is 0.2. The probability of A is equal to 0.6, and the probability of B is equal to 0.4. Oh, sorry, instead of given that, it should be determine if. That's bad. The given was on that line. Determine if. Good thing you use pencil. So determine if A and B are independent events given this information. Okay, so you're asked, are these independent? So you got to say, all right, what do I know about independent events? I know I'm going to use the formula P, A, and B is equal to P of A times P of B. So P of A and B is 0.2. So the question is that equal to 0.6 times 0.4? So put a question mark there. I don't know, are they equal? So 0.2, is that equal to 0.24? And we say, no. So we say these are not independent events, right? If they were independent, then they have to satisfy this formula. The probability of A and B is P of A times P of B. Okay, that's not true in this case. So they are not independent. Okay, what if? You are given that probability of A and B is equal to 0.56, P of A is 0.7, and P of B is 0.8. Are these independent? So yes or no, why? And they're independent because what?
Because 0.7 times 0.8 is 0.56.
Yeah. So another way that you could do this is just work this out, right? I'm just going to work P of A and B so you say for independent events, here's the formula. I'm going to plug in the P of A, the P of B, I get 0.56. That matches that. So yes, they're independent events. Okay, now if I was going to write a question based on that, I might give you like 4 events or 3 events or something and say how many of these are independent, right? Give you 4 events or 3 events, right? None of them are, 1 of them is, 2 of them is, 3 of them are, right? So that's a way to ask that. Anytime you're reading through questions and that, especially book questions, just ask yourself, how can you turn this into multiple choice? Like, is there a way so that, might I see a question that's kind of based on this question, but is asked as a multiple choice question? All right, 5 more. There are 3 children in the Smith family. Determine the probability that exactly 2 of them are boys. There are 3 determine the probability that exactly 2 of them are boys. Okay, so what is it? What's the answer? So this goes way back to lesson number 1. What is probability, right? It's favorable over total. So what's the total number of ways we can have 3 children in the family, in a family? Right, in terms of boys and girls. So the question is, how many ways are there that you can get 3 children in a family, and how many of those have exactly 2 boys? So we could draw a tree diagram. It's kind of the ugliest way. It's a little brute force, right? So like take a hammer to it and just beat it into shape. But that'll list, right? If we list all of the possibilities for a 3-child family, right, and there aren't that many. We should know how many, right? 3-children family, right? So it's 3 things, right? 1, 2, 3. Okay? How many possibilities for the first child? 2. Second child. Third child. So how many are there in total? 2 fundamental counting principle. First child times second child times third child. 2 times 2 times 2. 2 times 2 times 2. 8. Not plus, times. There are 8 possibilities. We could list them all. Right? Because we need to know, of those 8, how many have exactly 2 boys, right? Okay, so first child could be a boy, could be a girl. First one's a boy, second one, boy or girl. First one's a girl, second one's a boy or a girl. First 2 are boys, third one's a boy or a girl. Follow each branch, right? So we follow each branch unless this is boy, boy, boy. Boy, boy, girl. Boy, girl, boy. Boy, girl, girl. Girl, boy, boy. Girl, boy, girl. Girl, girl, boy. Okay, how many outcomes? 8. Good. Matches up with what we think from the fundamental counting principle, right? 2 times 2 times 2. How many of them have exactly 2 boys?
4.
There's 1. Where's the next one?
2 boys.
Where's the next one?
The first one and the girl.
That's got 2 girls.
Like that one.
Okay, anything else with 2 boys?
No.
Okay, so we've got what? 3 out of? The probability is 3 out of 8. Each of these probabilities is what? Think about it. This is probability going out this branch is a half. Out this branch is a half, right? And what's the probability of boy, girl? Not exactly a half, right? Slightly biased in favor of what?
Girl.
Or in favor of whom? Or which gender? Slightly biased in favor of boys because they do stupid things and kill themselves off. So we even out the numbers by the time you hit puberty and stuff, right? So as far as then it'll match out nicely. It is actually slightly boy. I don't know if that's the reason, but it is slightly biased in favor. Not much, right? We're not talking like 600,000 to 400,000. It's not 60-40. It's just slightly above. Each of these branches is half times a half times a half, or 0.125, right? I mean, there are 8 things. Each of these outcomes is equally likely. It's a fair game. Exactly. Each outcome is equally likely. 3 out of 8 is 0.375 is 37.5%, right? Probability 3 different ways. Fraction 3 out of 8. Decimal 0.375. Percent 37.5%. What else? Oh, now, if you could use the fundamental counting principle to count how many ways, right? So you just say, all right, 2 for the first child, 2 for the second, 2 for the third, 2 times 2 times 2 is 8. How can you figure out how to count how many ways have exactly 2 boys? What's the strategy? using perhaps your fingers instead of a whole big diagram. So if there's exactly 2 boys, what else is there?
One girl.
One girl. And where can she be in the family? She can be the oldest, she can be the middle, she can be the youngest. Right? Now if there's one she, there's 3 ways, right? If you've got exactly 2 boys, you have exactly 1 girl, who is either the oldest, the middle, or the youngest. So there's 3 out of 8. You don't need to do all this fancy stuff. Remember, it's multiple choice test. Nobody cares how you get the answer. However, do your work on the test, figure stuff out. Make sure you mark on the test, right? That you circle the answers of the questions, that you write in the numerical response. Just in case something happens, like you transpose number 1 into number 2, and then you get down to the bottom and say, I've still got 1 question, and I'm not going to go back and erase it. I'll just hand it in the way. Not a good strategy, if you ask me, but But if you then have to haul out the eraser and erase absolutely everything, you might be wanting to make an appeal and just say, you might want to look at that again. I did the best I could to erase it, but... Okay. I'm pretty sure that if the machine can't read your paper reasonably clearly, it'll just kick it out for somebody to look at. But then if you did erase, so number 1, or next piece of advice, mark all your answers in the booklet and do not mark your Scantron until you're done. Okay? So like when you're done, it's like I am ready to go, then the last thing you do is sit down and transfer your answers from the booklet to the Scantron. That way you're not going to make any mistakes, have to go back and say, oh, I need to erase that, and then worry about did I erase it well enough? Okay? Having said that, bring a good eraser just in case you do have to erase it. Blah, blah, blah. Okay, a couple more. Annie and Bobby are playing a coin and dice game. Each turn consists of rolling a regular 6-sided die and tossing a coin. So each turn sometimes in the interest of expediency or making the question a little bit faster, they might give you a 4-sided die, right? Because if you have to list the sample space for a 4-sided die, it's 2/3 the amount of work of a 6-sided die, right? There's only 4 outcomes. And sometimes they'll be able to give you a 20-sided die, but you won't be expected to list a bunch of outcomes, just use it in a calculation. Determine probability of rolling a 2 or tossing tails, but not both. Determine the probability of rolling a 2 or tossing tails, but not both. Okay, so we can roll a 2 or toss tails, but not both. So you could list all the possible outcomes, find out how many of them are rolling a 2, find out how many of them are tossing tails, but not count the one that's a 2 and a tails, right? We could do a little tree diagram, but we don't need to list every possible outcome, right? Think about what are we interested in? I'm interested in roll a 2. What goes down here? Roll a 3. Roll a 1. Well, that's come after the roll of 2. So I either roll a 2 or I don't roll a 2, right? So I don't care if I roll a 1, a 3, a 4, a 5, or 6. I care, do I roll a 2 or do I not roll a 2? So down here we'll just say, okay, you not roll a 2. After I've rolled the 2, then there's 2 things that can happen, right? I get a head or a tail. So head, tail, or here I get a head, tail. Now, following each branch is going to give us outcomes, but they're not equally likely, right? This is not a fair game in the sense of, hey, it's equally likely that anything happens. What's the probability I roll a 2? So what's the probability of this branch? 1/6. What's the probability I don't roll a 2? What do these two have to add up to? 6 out of 6, right? It's got to be 1. If I roll a 2, what's the probability I get heads? Probability I get tails. If I don't roll a 2, what's the probability I get heads? It's probability I get tails. So this is rolling a 2 and getting heads, right, will be 1/12. This is rolling a 2 and getting tails, 1/12. This is not rolling a 2 and getting heads, which is 5/12. And this is also 5/12. What do these guys have to add up to? They got to add up to 12 out of 12, right? Because that's supposedly I've listed every possibility. Okay, and I'm doing it in terms of rolling a 2. Now, what do we want? The probability of rolling a 2 or tossing tails, but not both. Okay, so am I going to count this? Is this rolling a 2 or tossing tails, but not both? Yeah, it's rolling a 2, but heads. Is this rolling a 2 or tossing tails, but not both? No, that's both, right? That's roll, think. Is this, so I want to roll a 2 or toss tails, so am I going to count this? No. Rolling a 2 or tossing tails, am I going to count this? So probability is 5 out of 12 plus 1 out of 12, 6 out of 12, or 1/2. Okay. So half the outcomes will be a 2 or tails, but not both. Another way you could do is you could sit down and list all the outcomes, right? Which is actually 12 of them, right? You get a 1 in a heads, or 1 in a tails, or 2 in a heads, or 2 in a tails, and so on. Okay, and then you can count. So there's many ways you can count this, right? This is just giving you some tools. Okay, last example. As soon as you two pay attention. Do the last example. We'll determine when we finish the course. Could be now, could be 6 days. Okay, Student Activity Council is having a raffle, and they sold 200 tickets. There will be 2 draws. After the first draw, the ticket gets put back. Okay? So there will be 2 draws. Look up here. Okay. So what kind of events are these? Okay, so they got to be independent, right? Because the ticket was put back. So after the first draw, the ticket is put back. I have purchased 4 tickets. For you, it's this spelling of the word I. I have purchased 4 tickets. determine the probability to the nearest tenth of a percent. Okay, so this could be a numeric response answer, right? It's got to be less than 100%. So you've got number, number, decimal, number. So determine the probability. If you have to do rounding in this question, when do you do the rounding? So when should you round in math? At the very end. Okay, so if you start rounding your intermediate answers, right? So if I got to work this out first, then I'm going to use that to work this. You're not going to get it right. Okay, you're going to bounce above or below at the decimal place. You'll just be one too high or one too low. Okay, so determine the probability to the nearest tenth of a percent that he will win at least one prize. So one of the things that comes into logic, set theory, counting, the puzzles, all of those, is reading the question and figuring out, okay, what's going on here, right? Like understanding, what are they asking me? What information are they giving me? What do they want me to find, right? It's George Polye's 4-step problem-solving method. Step 1 is understand. Okay, so if I will win at least one prize, how many prizes could I win? You can say the numbers. You could say them all. It's not that many. If I have to win at least one prize, I could win, or I could win. So if I have to win at least one, how many do I win? Or 2. It's at least one prize, right? If we don't get the idea of what does at least one prize mean, you're not going to go very far in this question, right? So we need to figure out that I've won one prize or both prizes. Now, maybe it's easier to work out what? That I don't win either prize, right? Because then the probability is 1 minus that. Okay, so you think about it. Right? What are the possibilities for one person? You could win one prize, you could win 2 prizes, you win 0 prizes. What's easiest to work out? Maybe it's easier to work out he doesn't win any prizes. Then subtract that from 1. Right? Because everything that's left would be winning at least 1. So give it a shot. See if you can work it out. Okay, I will pause this because it's going to take a while. Easiest way to work this probability out is to say that the probability is going to be 1 minus the probability of winning, of not winning both prizes, right? Don't win the first, don't win the second. What's the probability I do not win the first? 196 out of 200. What's the probability that I do not win the second?
196 out of 200.
Okay, so you go 1 minus 196 out of 200, right? So this is didn't win the first and didn't win the second. What's left? Everything else. What's everything else? Well, you won the first, or you won the second, or you won both. This works out to 0.0396. That's a decimal. Convert it to a percent. Multiply by 100. It becomes 3.96%. To the nearest tenth, 4.0%. Okay, got a 4% chance of winning first or second or both. Question?
What if you go 4% and just add
Man, you lucked into it, because that ain't the way to do it. Count yourself lucky. Nobody knows how you did it, so. Yeah, that's you're lucky, right? That's just all it is. There's no. That's kind of like saying 1 the first or 1 the second, and it works, but it's not right.